Okay, in chapter 8, we talked about a couple of really kind of big conversions or important conversions that you use a lot in chemistry. We also talked about atomic mass to begin with. And once again, you can get the atomic mass as the sort of number that's below the symbol on the periodic table. And we can use it sort of as two little bit different units, but you can say, for example, there's 1.008 AMU and an atom of hydrogen, which would be the number that you would find underneath hydrogen on the periodic table. And AMU is atomic mass unit. It's a unit of atomic mass. And it's really, per se, not necessarily a convenient unit that we use a lot. We talked about how to calculate the atomic mass. And what we do see on the periodic table are the average atomic mass of all the naturally occurring isotopes for that particular element. And remember, you kind of do the, if you wanted to calculate it there, you take the percentage of the first element, or sorry, isotope, times the atomic mass of that first isotope, plus the percentage of the second isotope, times the atomic mass of the second isotope, and you just kind of continue that pattern. Now, a more sort of convenient unit that we do pull off the periodic table is one that involves grams, and that revolves around moles that we also talked about. And a mole of something, which is abbreviated MOL, is equal to 6.022 times 10 to the 23. And these could be atoms, they could be molecules, for example, could be really any type of unit. And this is what is known as Avogadro's number. And Avogadro's number is sort of the conversion factor that we use to go between really those two units. If we need to go from moles to atoms or molecules or backwards, it really is Avogadro's number to do that. So moles to atoms, or again, they could be molecules heading back and forth. That is what we want to use as a conversion factor. As we talked about last time, you really do want to avoid using Avogadro's number unless you really are doing that conversion. So usually that means you have some type of number that's given to you in atoms, some type of numbers given to you in molecules, or you're asked to solve for one of those. Otherwise, you really shouldn't use Avogadro's number. And sometimes people want to use it like in every calculation, but it really is specific for sort of that conversion. Sort of the number that we do use a lot and sort of a better version, if you will, of the atomic mass is what is sometimes referred to as the molar mass. And the units of molar mass are grams per mole, which is a more useful unit for us because a lot of times we do end up with mass in grams. And basically, we could also pull off that number from the periodic table. And we could pull it off as there would be 6.941 grams of lithium per mole. And we really could use it as a conversion factor, molar mass. We could use it as grams per mole, or moles up on top per gram, or per gram there. And it's important that when you do calculate the molar mass, the number always stays with grams and it's always 1 mole. So it's never more than 1 mole when you're doing the molar mass. And when you calculate the molar mass of something, it is based solely on the actual formula. So basically, if it's just one element by itself, you just go to periodic table, get the molar mass. If it is multiple sort of elements together in a compound, use the formula, basically just add up all the parts. And when you add up all the parts from the periodic table, that's how many grams per mole there are in that particular substance. But it's really important. It is always 1 mole and its number always stays with the grams part of it. And this is a really important conversion, really factor as we do the conversion between grams to moles or backwards a lot in chemistry. So most of the time, a lot of the time, when you're doing those conversions, you just go to the periodic table and use it as a conversion factor. So again, if we had multiple things like in water, to get the molar mass of water, we would just add up all the parts. So there are 2 times 1.008 grams per mole plus 16 grams per mole from our oxygen there. Gives us something like 18.02 grams per mole is the molar mass of water. And again, that's really a conversion factor that we use. So we can set it up dimensional analysis way and solve for either grams or moles, depending on what we are looking for. That's where we kind of laid it up. Any questions on any of that there? All right. I'm not sure if that meant a question or not, but that's it. All right. So I think, did we not do this one? We did or did not do this one? I don't think we did this one. So why don't we do this one? What is the mass in grams of one gold atom? The molar mass of gold is 197 grams per mole. Take a look here. So in this case, we're looking for the mass in grams of one gold atom. So the key here is obviously the rest of it may not be given to you, but atom means at some point we should probably use Avogadro's number here. And the pathway here is we'd want to go perhaps from atoms to moles, as Avogadro's number would do that for us. And then from moles to grams using the molar mass. So those are really the two sort of conversion factors and pathways is going to allow us to do that. We would, if it obviously wasn't given to you, which it probably would not, go to the periodic table there and find the molar mass for gold. And obviously we do need to know Avogadro's number, which is our 6.022 times 10 to the 23. So we'll start with the one gold atom. Once again, using Avogadro's number as a conversion factor, that means the atoms need to go on the bottom so they cancel. So at this point, the atoms of gold would cancel. And if we stopped at this point, we would be in moles, which again gets us really to this point of the calculation. So we do need to go to the periodic table. And once again, that is where we find that number of 197. Remember that we do pull about 4 significant figures typically from the periodic table when we use it. And that means that there's 197 grams per mole of gold. Or again, if you needed to use it the opposite way, a mole would have 197 grams. So you could use it really either way. In this case, we actually need the moles on the bottom. So we'll use it in this fashion. And a mole of gold would be 197 grams. The moles of gold would cancel, and that's going to leave us grams, which is good. So basically here we're taking 197 and we're dividing it by Avogadro's number, making sure you use the exponent button. And if you hit the right button would help as well. And we'll get something like 3.271 times 10 to the minus 22 grams in this case. Any questions on that there? In terms of the sig figs, because 1 is technically something you would count, you could pretty much do any sig figs you want. So I went with 4 based on the molar mass that has 4 significant figures. Question on that calculation. Bless you. All right, let's skip down. Why don't we do these two here? We're looking for how many moles are there in 23.2 grams of ethanol and how many molecules are there. And I'll give you some periodic table stuff. 12.01 for carbon, hydrogen 1.008, and oxygen there 16. All right, take a few moments and knock out both of these here. Okay, let's take a look. So first one there is we want to know how many moles and grams. So this really, again, is a grams to moles conversion. And remember, it's the molar mass from the periodic table that allows you to do that. In this case, we need to figure out the molar mass here of this compound. We're just going to add up all the parts. So there are 2 carbons, each are 12.01 from the periodic table. There are 6 hydrogens, each are 1.008 from the periodic table. And there's 1 oxygen, which is 16 from the periodic table. So this is our carbons, our hydrogens, and our oxygens, basically. And if we do all that here correctly, which would be good here, let's see. Looks like 4607 here grams per mole. Remember, so this is really our conversion factor. And again, we could use it with the grams up on top, moles on the bottom, or if we needed to, we could flip it to show our dimensional analysis. In this particular case, we are going to need to flip it as we are starting with 23.2 grams of our ethanol. Once again, we do want the grams to cancel, so we're going to put the grams on the bottom. That will cancel out our grams. So we're basically taking 23.2, we're dividing it by 46.07. Gonna give us something like 0. Looks like 504 moles here of C2H6O. Any questions on that calculation there? So the second part here is how many molecules are there in 23.2 grams of ethanol. So really it's kind of a continuation of the first part there. So since we do have moles, we kind of want to go from moles to molecules. And a reminder that to do that, that is Avogadro's number that's going to allow us to do that. So remember, it's a constant pretty much. You got 6.022 times 10 to the 23 molecules per mole. And once again, here you can flip it around the other way if you need to in the calculation with the moles on top, the molecules on the bottom. So we'll actually continue on here with the number that we got, which is basically what we would have to do first if we were doing this problem from scratch. So this is our moles of C2H6O. In this case, we could actually use it just the way it is there, Avogadro's number, and that's going to give us 6.022 times 10 to the 23 molecules per mole. Again, the moles will cancel out, times in it by Avogadro's number, making sure again to use your exponent button. And don't add anything else to it. There we go. Gonna get us a, we'll call it 3.03 times 10 to the 23 molecules of C2H6O. Any question on either of those calculations there? Although we are using Avogadro's number a lot, again, molar mass probably more commonly used in a lot of calculations that you do. Any questions on that there? Okay, let's try one more here just to make sure. What is the mass in grams of one molecule of caffeine? So again, from the periodic table, carbon 1201, hydrogen 1.008, nitrogen 1401, and oxygen still 16. All right, we're looking for mass in grams of one molecule of caffeine. Okay, so once again here, we're looking for grams. We're starting with molecules. So molecules is the key word that makes us think that we should probably be using Avogadro's number here somewhere. Our pathway here is going to take it from molecules to moles. And remember, again, that is Avogadro's number. And from moles to grams, which is our molar mass number. So at some point here, we will need the molar mass of this guy. So we're going to add up all the parts. That's going to be 8 times our carbon molar mass, which is 12 grams per mole, plus 10 times our hydrogen's molar mass, which is 1.008 grams per mole, plus 4 times nitrogen's molar mass, 1401 grams per mole, and finally 2 times oxygen's molar mass there. And if we do all that, I believe it says 194.2 grams per mole is the molar mass. Stop any questions on that there. So basically just adding up all the parts. And in this case, though, we are going to start with Avogadro's number because that is going to take us to moles. So starting with 1 molecule. And again, here we are using the units of molecules because that is what caffeine is in this case. Using our Avogadro's number. In this case, we do want molecules to cancel. So we're going to put Avogadro's number on the bottom here. And that would be 1 mole of it up on top. Again, the molecules would cancel. At this point, if I stop the calculation, I would be in molecules, which is almost there, but we do want to use the molar mass that we just calculated to take us the whole way. So in this case, because I set it up with dimensional analysis, I can see moles are on top. So when I use the molar mass, I want the moles on the bottom here so that they do cancel. And again, the moles here will cancel, leaving us with grams. And that would get us basically 194.2 divided by 6.0222 to the 23. About 3.225 times 10 to the minus 22 grams would be 1 molecule of caffeine. Any questions on that calculation there? Question on molar mass, Avogadro's number, grams to moles, moles to grams. Okay, one thing we're going to talk about here before we kind of move on to the next little topic is now in a lot of these examples we just did, we were interested really in sort of the whole thing, this entire sort of compound, if you will, or molecule, or just the element by itself. Now, sometimes when you're dealing with a molecule like this, they may be interested in maybe just one of the elements of it and not necessarily the whole thing. So you do have to do a little bit of a different calculation or think about how you could get to what you're looking for. So let's take a look at an example here. Let's say we had 25.6 grams. We'll do the one we kind of did earlier there of ethanol. And we wanted to know how many grams of hydrogen would that be? Now, in this particular case, we're not interested in the entire ethanol there, the C2H8O. We're interested in really just the hydrogen part. So along our sort of pathway here, we need a way to go to basically just the hydrogen part. And one way that you could do that is actually use the formula itself as a conversion factor. So when we look at this sort of formula of C2H8O, all the numbers on the bottom does tell us how many of each of those atoms they are, but they're also considered the moles of each of those. So those are really considered the moles of each of those elements that are present. So what we could actually do is from any sort of formula like this, we could actually write several kind of conversion factors just using the formula itself. So for example, we could say in 1 mole of this entire thing, there would be how many moles of carbon? There would be 2 moles of carbon. We could also say in 1 mole of this entire thing, there would be 8 moles of just hydrogen. And lastly, in 1 mole of this entire thing, we could say there would be just 1 mole of oxygen. So each of these are sort of equalities, and you could actually write 2 conversion factors for each of them that are there. Obviously, a mole on top and mole on the bottom of each element and flip it. So we could use that to go from really the whole thing to the individual element. So we do want to think about where we're starting. We have grams of the entire thing. But in order to use this relationship here, which is the one we would want to use, we do need moles. So we actually have to go to moles of the entire thing. And that's going to require the molar mass to do that. And once we have moles of the entire thing, we could use our formula relationship here to go to moles of hydrogen. And once we have moles of hydrogen, we could go to grams of hydrogen using the molar mass. So that's sort of our pathway that we could kind of get to what we're looking for. And again, it is sometimes common that you're interested in maybe just one of the elements that are present in a molecule. So to do this, we'll use the same molar mass we calculated on the previous problem, which if I remembered would be great, but I think it was 94 and some change, I think. Or 4808. So this is, we saw earlier, 4808 grams per mole, I hope. So we're going to first use that to convert it into moles, and that's going to allow us to use our formula's conversion factor. So starting with 25.6 grams of the entire thing, using the molar mass of the entire thing here would give us 4808 grams per mole of the entire thing. Once again, if we stopped here, we're in the whole formula. This is where our sort of conversion factor that we got from the formula will come into play. So we'll use that next. And that would give us in 1 mole of the entire thing from the formula, we could see that there are 8 moles of hydrogen. So that is our conversion that's going to allow us to go from the whole thing to just hydrogen in this case. Lastly, here we are interested in grams. So we're going to take our molar mass of hydrogen only in this case from the periodic table. Those guys are going to cancel, and that would get us 25.6 times 8 times 1.008 divided by 4808 equals that. So that will get us that there are 4.29 grams of hydrogen in this case. Any questions on that? All right, so why don't you try one here? We'll use the guy we just did on the previous one. We got a little bit of that there. So some of this here. All right, so let's say how many nitrogen atoms are there in 136 grams of nicotine, or not nicotine, caffeine? All right, give it a go, see what you come up with. Okay, so a couple important sort of words in this problem. First off, I do see atoms, which makes me think I should probably need to use Avogadro's number somewhere to get to atoms. I also see that I'm just looking at nitrogen, again, not the whole thing. So it makes me also think I need to use the formula as a conversion factor to help us get there. So we can see from the formula that in 1 mole of the entire thing here, and since we're interested in just nitrogen, we get 4 moles of nitrogen. And again, that comes from right there, as that is the number of moles. So once again here, we are starting with the whole entire compound, and we need to get to just nitrogen in order to use that relationship that I just wrote up on top. We got to get everybody into moles. So that's really the first step that we would want to do here, is to convert our grams of the entire thing into moles. So we'll do our entire thing's mass. We'll use the molar mass that we calculated earlier, which is 194.2 grams. That is going to cancel out the entire grams, and now we're into moles of the entire thing. That is what's going to allow us to use our relationship from the formula here to go from the entire thing to just nitrogen. So if we do that, we again see from the formula 1 mole of the entire formula. We get 4 moles of nitrogen in this case. Any questions on that so far? If I stop my calculation here, I'm actually in moles of nitrogen. Now, in this case, we're actually looking for atoms of nitrogen. So we want to go from moles to atoms, and that is going to be Avogadro's number. That's going to allow us to do that. So here we actually do not need the molar mass of nitrogen, but we do need Avogadro's number. And in 1 mole of nitrogen, there would be 6.022 times 10 to the 23 atoms of nitrogen. The moles of nitrogen will cancel each other out. Once again, here, punching it in, making sure we use our exponent button, multiplying what's on top, 136 times 4 times 6.022 to the 23. Hit equals, then divided by 194.2, going to get us a bunch of nitrogen atoms, which is something like 1.69 times 10 to the 24 atoms of nitrogen. Any questions on that one there? So these are a couple of variations sometimes on these type of problems where, again, you kind of have to use the formula as a conversion factor. Any questions on any of those calculations? Okay, then let us continue rolling here. The next thing we're going to talk about are molecular formulas and empirical formulas. So first off, a molecular formula pretty much tells you exactly what's in there, what's in the compound, our molecule. So it tells you exactly how many atoms of each element are present. And a molecule, obviously, as we talked about, is really an arrangement of 2 or more atoms together. Compound, once again, is a combination of 2 or more elements that are together. A chemical formula, as we talked about, basically expresses the elements that are involved. And a reminder again that it is the subscripts, right, that tell us, in this case, as we just saw, how many moles or how many atoms of each element are there. And once again, the subscripts always go to the guy to the left. And if there is no subscript, it's assumed to be 1, right? So a molecular formula, again, tells us exactly what is present. And now molecular formulas can be a variety of ways that they are written. Sometimes molecular formulas will frankly not really give you any information about how everybody's sort of connected. Just basically tells you what's there. And sometimes chemical formulas will give you, or molecular formulas will give you some information about how things are connected to each other. So for example, this guy here is a molecular formula there for acetic acid. This formula also is sometimes written C2H4O2, which is also acetic acid. If you count up basically what is present in both of those formulas, they both have 2 carbons, 4 hydrogens, and 2 oxygens. The bottom formula or molecular formula pretty much just tells you what elements are involved. The top one here actually gives you some structural information about how things are sort of connected. So if you were to draw this, it looks something like this. And as you can see there, this is CH3. And this part here is the COOH part of it, which is a special organic group, which is known as carboxylic acid. So that molecular formula gives a little bit more information about basically how everybody is connected. And by the way, in case you're curious, it is that hydrogen that makes it an acid. It comes off when it is acting as an acid. And then once again, just kind of tell you what is present. Same thing here with ethanol. These are two formulas for ethanol. They both have the exact same number of carbons, hydrogens, oxygens. The bottom one here also gives you an idea as to how it's connected. So, you know, it basically looks something like this. And once again, that sort of bottom formula does give you a lot of that information. This being the CH3. This being the CH2 part. And lastly there, you can get it maybe. This guy here being the OH part. So again, sometimes those molecular formulas will give you a lot of information about how it's basically connected. And again, in the basic form, it will tell you exactly what is present. And that is different than the empirical formula. Now, the empirical formula is really the simplest whole number ratio of what is present. So the empirical formula doesn't necessarily always tell you what is present, like the molecular formula, how many of each of the elements are present, but it gives you that simplest whole number ratio of what's present. As we can see here, H2O2 is the molecular formula for hydrogen peroxide. That is 2 hydrogens for every 2 oxygens, which basically if you divide by 2, it's the same as 1 hydrogen for every 1 oxygen, although that looks like a 10, which gives us an empirical formula of HO. If we had something like C2H6 as the molecular formula, we could look at this and see that that is 2 carbons for every 6 hydrogens. Once again, in this case, we could divide everybody by 2, which gives us a ratio of 1 carbon for every 3 hydrogens that are present. And that would give us an empirical formula of CH3 in this particular case. So the empirical formula is always the simplest whole number ratio, and that's important. It does need to be a whole number ratio of what's present. So if you could not reduce down everybody by a common number and still get whole numbers, then you shouldn't do that. So sometimes the molecular formula, say for water, that is 2 hydrogens for every 1 oxygen. In this case, you cannot reduce this down anymore and still get a whole number, which means both the molecular formula and the empirical formula in this case would actually be the same. All ionic compound formulas are empirical formulas because when we put them together, the positive charge and the negative charge, we put them together so they equal 0 in the simplest way possible. So whenever you look at an ionic compounds formula, a metal and a non-metal, cation and anion, they're always really empirical formulas. There's also the molecular formula as well, or a formula unit, I guess, in that case, because it's not really a molecule. But they're really all empirical formulas because you should put them together in that simplest fashion. So molecular formula tells you exactly what's there. Empirical formula tells you the exact sort of ratio of what's present. So once again, here's another example, N2H2, that is 2 nitrogens for every 4 hydrogens, gives us an empirical formula of NH2, in this case by simply reducing everybody down here by 2. Again, only the molecular formula tells us the actual number of atoms. The empirical formula is that simplest chemical formula. They're always written to convert the subscripts of the molecular formula into the smallest whole numbers. A lot of times in the lab, if you're doing an experiment, you are sometimes easy to figure out the empirical formula by simply taking differences in mass swings, and you could calculate the empirical formula pretty easily in the lab. So as I mentioned before, some molecules do have both the empirical formula and the molecular formula being the same. Again, in the case of NH3, that is 1 nitrogen for every 3 hydrogens. No way to reduce that down any further. Same thing with CO2, 1 carbon for every 2 oxygens. That is, again, as simplest as you can get it, and you cannot reduce it down any further. All right, so take a moment here and lay up the empirical formula for each of these. This first one here, we have basically 2 carbons for every 2 hydrogens. You clearly can reduce those guys down by 2, which would basically give you 1 carbon for every 1 hydrogen. So the empirical formula there would be CH. Looking at the second one here, that is 2 iodides for every 5 oxygens. There's no way to divide that out and get a whole number, which obviously a formula needs a whole number for the subscripts, which means the empirical formula would be the same in this case as the molecular formula. Any question on those two? Lastly, here we have glucose, which is 6 carbons for every 12 hydrogens. For every 6 oxygens. You could probably see you can divide everybody here by 6. Gives us 1, gives us 2, gives us 1, which are all whole numbers, which means the empirical formula here would be CH2O in this case. Any questions on that? So this is sort of a simple way that you could calculate the empirical formula if you are given the molecular formula and you want to reduce it down. We're going to talk about in a second here how to calculate it with some other information. But before we do that, let's first talk about another important aspect, which is the percent composition by mass. So we can, and it's not, should be multiplying there. So we could calculate the percent composition by mass by basically taking to figure out the percent of each element present, we take the mass of the element in that particular formula divided by the molar mass of the formula times 100%. So we could calculate the percent composition of each element in a compound by using the molar mass and really taking the mass of each of the elements that are there. Kind of very similar to how we figured out the percent of water in those hydrates that we did the other day. We took the mass of the water divided by the mass of the entire compound. Here we're just going to take the mass of each element and divide it by the mass of the entire compound. And obviously to turn it into a percentage, we want to multiply by 100 in this case. So if we take a look at one here, like our hydrogen peroxide, the first thing that we would want to do is get the molar mass here of the hydrogen peroxide. So we're going to go to the periodic table and add up all the parts. So that is 2 times 1.008 for our hydrogens, plus 2 times 16 for our oxygens. That is going to give us a molar mass here of 2 times 1.008 plus a 3402 grams per mole. So we can now figure out the percentage of each of the elements that are present. So if we did the percentage of hydrogen, in the case here, we have 2 hydrogens at 1.008 grams per mole, divided by the molar mass of the entire compound. And we're going to times it by 100% in this case. And that would give us 2 times 1.008 divided by 34.02 times 100. Going to give us 5.926% hydrogen. Now we'll do the same thing for our oxygen in this case. So the percent of oxygen is in this case 2 times 16 grams per mole, as there's 2 oxygens in that compound divided by the molar mass of the entire compound times 100% in this case. So taking 32 divided by 34.02 gets us about 9406% oxygen. Any questions on that? Yeah. By the way, once I actually have the percentage here of hydrogen, I can figure out the percentage of oxygen by doing what? Yeah, because there's only one other element present. I could take 100 minus that, right? The percentage of hydrogen. You could also get yourself there to the percentage of oxygen, since there's only 2 obviously here as well. And all the percentages obviously should add up to 100% because they're made up of those 2 elements in this case. Any questions on that? Again, with rounding, you might get 9407 or something like that, but pretty close. All right, so let's take a look at the empirical formula here for hydrogen peroxide, which is HO. So why don't you calculate the percent composition of each element here in the empirical formula? All right, so we approach this the same way. We're gonna get the molar mass. In this case, it's just HO, so that's gonna be 1.008 grams per mole for the hydrogen and 16 grams per mole here for the oxygen, going to get us 17.01 grams per mole. So our percentage of hydrogen here in this case would be 1.008 grams per mole divided by 1701 times 100%, and that will get us give us 5.926%. And we'll do the same thing here with oxygen. In this case, just 1 oxygen, 16 grams per mole, 1701 grams per mole times 100%. And 16 divided by 17.01 times 100, 9406. Oxygen. So we could clearly see in this case that is majority made up of oxygen, but more importantly, between the molecular formula, which was here, and the empirical formula, are the percent compositions the same or different? They are the same, and that's because obviously the empirical formula is based on the molecular formula. It's just the simplest ratio of what's present. So if you have the same ratio of masses, right, you could get the same percentages that are present. So you can calculate the percent composition between the molecular formula and empirical formula. They should come out the same. To 4 digits. Yeah. Yeah, so in general, like we talked about a couple of things, in general, when you do pull the number off the periodic table, you typically go to 4 significant figures, and typically, in general, when you calculate the molar mass, 4 significant figures is typically what you would go to. And that's really the basis why we kind of rounded our percentages to 4 significant figures as well. Yeah. Yeah, so pretty much that's usually the amount of numbers that you should use on most cases when you're doing molar mass. Other questions? Okay. So we do see the percent composition, obviously, for each of these elements would be the same regardless of the molecular formula or empirical formula, because they're basically just ratios of each other, which means you'll have the same sort of proponent or composition of each. Any questions on that there? All right, we will lay it up there for now.